Hi, this is Mark Sarazano from the International Piano Technician School, and I'd like to share with you the old school Perfect 12th test, the way it was originally taught to me. And I would like to present to you the idea that piano tuning, as a craft, has a problem. It is being taught in a far more difficult way than it needs to be. Let me show you what I mean. I was originally told that in order to tune the treble accurately, I should tune the double octave as wide as the fourth. Let me show you what that means. The double octave here, F3, F5, is wide because the F5 is higher than the fourth partial of F3. That's what makes it wide. But how can we measure this? We use a check note. C#3 has the same coincident partial as F3 and F5. And when the piano is remotely in tune, the C#3's F5 will be lower than the F3 and F5's F5. Playing C#3 with F3 produces a major third, and it creates beating that indicates, now listen, this is important to understand. If you want to understand how check notes work, you have to understand this concept. Playing C#3 with F3 creates beating that indicates how high the fourth partial of F3 is above the fifth partial of C#3. If the fourth partial of F3 is at the same frequency as the fifth partial of C#3, there will be no beating. But because it's a little bit higher on purpose, that's how we set the C#3, that's how we set check notes, there will be beating that indicates exactly how high that fourth partial of F3 is. Let me state that again in more general terms. When you play a check note with an interval note, you are listening to how high the coincident partial of the interval note is above the fifth partial of the check note. Similarly, when we play the C# with the F5, we're going to be hearing how high the F5 is above the fifth partial of C#3. Now we can compare each of the F5's height above the C#3's F5. The speed of the major third indicates the relative height of the coincident partial above the C#3's F5. Similarly, the speed of the major 17th indicates the height of F5 above the C#3's F5. By playing them back and forth and comparing their beat rates, we can determine the relative height of each of the coincident partials. The fact that the 17th is faster than the third indicates that the F5 is higher than the F3, and when the top note is higher, we say it's a wide interval. Now we can do the same thing with the fourth F3 A#3. We call it a 4-3 because that's where the partials line up. That's where the beating will occur if the P4 is not pure. This perfect fourth is obviously wide because the third partial of A#3 is higher than the fourth partial of F3. There is beating at the 4-3 because it is not pure. The top note A#3 is higher than what would be a pure P4 with no beating at F5. But how can we measure this by ear? You guessed it, a check note. We will use C#3 again, because it shares F5 with F3 and A#3, and its F5 is lower than the other F5s, on purpose. As we've already seen, playing C#3 with F3, the major third, creates beating that indicates how high the fourth partial of F3 is above the fifth partial of C#3. Now, playing C#3 with A#3, the major sixth, creates beating that indicates how high the third partial of A#3 is above the fifth partial of C#3. Now we can compare each of the F5's height above C#3's fifth partial, F5. This means that the fourth partial of F3 is lower than the third partial of A#3. F3 is lower than the pitch that would make the perfect fourth pure. F3 is the bottom note, so F3 A#3 is a wide perfect fourth. But wait, the double octave is wide by the same amount that the perfect fourth is wide. That means that the 12th is pure. This was proven with the tests major third slower than major sixth, that proves the wide fourth, and major third slower than the major 17th, proving the wide double octave. If the difference between those beat rates is the same in each case, that just makes the major sixth equal to the major 17th, the test for the pure 12th. This just goes to show how a simple idea like testing the 12th to be pure using the major 6th and the major 17th to test that the 3-1 perfect 12th is pure was originally so complicatedly explained that it must have made many beginning piano tuners' eyes glaze over. Piano tuning does not need to be this complicated. If you would like to learn how to tune using a very simple way that, because of its simplicity, has allowed piano tuning students to achieve concert level piano tuning results in a matter of months instead of years, then reach out, email me at mark@howtotunepianos.com, and I will share with you how this system that I've created has been able to get piano tuning students results that they never thought were possible, which has allowed them to discover a career that is able to give them all the things they were hoping for. Thanks for watching.